talks that I've come to. And I'm glad that you all could find time on these busy days to come and some views on what happens when quantum technology will start invading game theory. So we're going to start with a classic, and I have to say that for whatever reason, I'm sharing the screen, but my program is not running. Let's see, there we go. We're going to start with flipping coins with Picard and Q. Picard's going to be our classical representative, and Q, of course, being from the Q continuum, he'll represent the quantum world. So the story begins as all Star Trek stories go. Some existential crisis is threatening the Enterprise. All looks lost, and who should appear on the bridge behind Picard but Q. Q offers to save the Enterprise if Picard can prove himself worthy. And the way that Picard can prove himself worthy is by beating Q at a little coin flip game, which we'll describe now. So our two players will, they have a coin. It's in a little box that they can look at, and it's in the box heads up. And it has two orientation states, heads and tails, which Q shows to Picard. And as far as Picard is concerned, it's just a coin. So what happens then is the play of the game goes like this. The box is closed in the initial state heads. Q then gets to perform an operation on the coin that Picard doesn't know. Picard gets to then act on the coin in a manner that Q doesn't know. And then Q gets to act on the coin another time, and again, a matter unknown to Picard. Then what happens? Well, we open the box and the coin is examined for orientation, heads being a win for player Q, while tails is a win for player Picard. And the deal is that if Picard wins, Q will save the Enterprise and all aboard. And if Q wins, Picard will just have to deal with his and his crew's fate on their own. And of course, Q can't give up on a good thing. So to make it more tempting to Picard, he offers to play Picard 10 times. And if Picard can beat him even once, Q will be happy to save the Enterprise. Okay, if you have any questions, I'm going to ask you just jump right on in. You know, I can't really see if people are waving their hands or if they're asking me a question via chat. So feel free to just jump right in if something isn't 100% clear.
So does perform an operation, that means, by that you mean anything? Like, so Q can do...
for example, he could flip it over or he could leave it alone.
Okay.
Okay, so some physical thing, you'd shake the box. That's what perform an operation means.
Better, thanks.
Okay, all right, so let's take a look at what Picard thinks is going on. So as far as Picard is concerned, here's what he believes. Picard, being a StarCraft captain, of course, had to take game theory at Starfleet Academy. And if he hadn't done real well, he would never have advanced to being a captain. So Picard thinks a little bit and says, well, what can happen to the coin? Well, the coin either stays in the same state, that's no flip, or I can flip the coin over. That is, heads goes to tails, tails goes to heads. So those are the two operations on the coin that Picard thinks is going on. These are the ones that change the orientation. Exactly how they're manifested doesn't really matter because this is the effect of the action. Picard knows he can act once and he can choose either no flip or flip. That's what you see in the first column are his strategic choices. And across the row at the top are what Picard believes to be Q's strategic choices. He can either not flip the coin on two chances to act, or no flip, 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 no flip, or flip both. And then Picard very quickly says, all right, this game looks awfully symmetric. Half the time I win, half the time Q wins. So far so good. So Picard also knows that there isn't really an optimal strategy here, but Q might be able to read him somehow. So in order to defeat that, Picard thinks that the thing to do is to have a random variable choose his strategies for him. So he knows he can win half the time by playing his two strategies just by flipping a fair coin in a way that Q can't discover the result and have that determine a strategic choice. So as we'll see when we get into the game theory part of this talk, this ensures that Picard wins half the time, no matter what Q does. Q, the best Q could do to guarantee a number of wins, well, he could win half the time if he plays his four strategies a quarter of the time each. These uniform strategies being something called a mixed equilibrium. Okay, so far so good? By your silence, I'll say go forward. All right, so Picard figures that since he can win 50% of the time, to lose 10 times in a row, well, there are 1,024 possible 10-game trials, only one of which is lose all 10. So to win only once, Picard is 1,000 to 1 favorite. So Picard says this is a pretty good idea. This just must be some face-saving gambit on Q's part to help the Enterprise out. Well, but no. Picard loses every time. Well, the odds on that were pretty long, so Picard starts to protest. Q, of course, just says Picard is miserable. And look, I'll prove it to you. We'll do this 25 more times. Anytime you think I'm cheating, mon capitan, you just open up the box and look, and we'll just play that one over. And again, all Picard has to do is just win once. Okay, so we proceed. Picard, all the time, makes several choices to observe the coin after Q's first move. And what he does is he sees the coin in orientation heads about half the time. Excuse me. And it tails the other half. This is entirely consistent with Q playing that optimized classical mixed strategy. But again, Picard loses every time. And of course, Picard loses the Enterprise in the process. Q doesn't save them, but at least Picard and the crew escape. In the escape pod, waiting rescue, Picard has a long time to think about this game. And figuring that, you know, he has a 50-50 chance of winning each time, losing 25 times in a row is pretty thin. 1 in 33.5 million. So he must have been cheated. But how? Well, Picard is being cheated, but it's a quantum thing. Picard isn't being told everything. You see, the coin in this little game is anything but a classical quarter that you might flip and decide comes up tails, the two orientation states. Q knows, in fact, this coin is really a quantum bit with respect to the orientation basis, heads and tails. So what that means is that there are lots more orientation states that this quantum bit can be in. Indeed, there's an orientation state for each point on the surface of a soap bubble, the so-called Bloch sphere. And in the Bloch sphere, we can think of heads and tails. We can think of these the north and south poles of this sphere. But it also means that there are lots more things that can happen to this quantum bit than just the no flip and flip operations that Picard believes are possible. For example, any rotation of the soap bubble, classically there are 3 of these, once around the x-axis, once around the y, once around the z. These are called the Pauli rotations. Any rigid motion like that is something that Q could do to change the state of this coin away from heads and tails and into something, a state that is really quite different. Okay, so if you don't know about quantum mechanics, this might be a postcard from Mars. So I thought I would have Marvin write it to you. And so to understand exactly how beautifully this scam works, you have to understand at least the basics of quantum systems. All right, I'm a mathematician, so I like axioms and theorems. In other words, there are things that are just true, and we figure out everything else by connecting a logical argument to them. Well, if I was a physicist, you'd be real unhappy with the axioms I gave you. They are pretty complex mathematically, and it can take a long time just to kind of digest what any one of them says. But we have the advantage that we're not using the full physically quantum system that we build quantum computers are. In quantum computation, we actually use a very small subsystem. And that means that I can tell you these axioms, and you can actually understand them without undue pain. All right, so what do these axioms look like? The first one, or the first couple, are what's called the coordination axioms. This is how we keep track of everything. So the first one you can probably guess, and that is that quantum systems exist in states. One and only one state in any given instant. Whatever a state is, a quantum system can only inhabit one of them. And they change in various ways and through various rules. And those will be something called the state evolution axioms. But of course, we like to be able to keep track of the numbers. And if not numbers, arrays of numbers. And so that comes the second axioms. That means we can actually give each state a numerical locations. So this is something that we call coordinates in mathematics. And we do this by employing something called a complex projective Hilbert space. Well, okay, folks, I appreciate that we're all very unhappy now because that doesn't sound elementary at all. So allow me to apologize. And let's see if I can unwrap what we mean by that in a way that everybody can lay their hands on. All right, well, let's start with complex. Complex refers to a number system. And complex numbers are, some of you are probably familiar with them. We get them from the real numbers just by what's called Dixon doubling. That is, we introduce an imaginary number, which we call I, and no offense to my colleague, Professor Perkowski, the electrical engineers like to call this J, but we'll forgive them. The square of I is -1, which is something a real number does. Well, then what we do is we just formally add numbers together. Take a real number A and take a purely imaginary number B times I and add them together by putting a plus sign between them. They just work. And so then, if you remember your algebra class from the Dark Ages, we just treat that as a polynomial and add them and multiply them that way. Geometrically, though, it's a little bit nicer to see. I can think of a complex number as a point in the plane. And so that point in the plane is some distance from the origin. That's its real length, r. And that line between the origin and the point in the plane that represents my complex number, well, that makes an angle theta with the positive real axis. Then in this configuration, to add two complex numbers together, I just put the tail of one at the head of the other. And to multiply them, I just then multiply the lengths, and then I just add the angles. So either way, this is a number system that is bigger than the real number system, twice as large in fact, and has some really nice algebraic properties which are really useful in quantum mechanics. Now, I should point out that there is an important subset of the complex numbers that arise a lot, and those are the numbers that have length 1. That, of course, is the circle centered at the origin. And the nice thing about these is that they're closed under multiplication. If I have two complex numbers of length 1 and I multiply them, well, 1 times 1 is 1. That means I get a third one. And that third one, of course, I get just now by adding the angles. So these numbers have this really nice property that there's a way to turn multiplication into addition, which you might remember from your algebra class is something all good exponentials do. That will be a very useful thing to know. Okay, so probably everybody now needs a deep cleansing breath. I'll take one. And allow me to once again encourage you, if I start saying things that aren't clear or that you'd like some more explanation to, please just pipe right on in. It won't bother me again because I'm not seeing the chats. And I might remark to Mark that it looks like there are 6 more people waiting outside. So, whatever.
Oh, I don't see anyone waiting.
Okay, 26 participants and 6 more outside.
I don't see the
my
outside.
screen is showing. Oh, 6 chats. Sorry, I'm not seeing the chats. Sorry, my mistake. Allow me to apologize and go forward. Let's talk about Hilbert spaces. What could this possibly be? Well, Hilbert spaces, they're just collections of what we've been calling locations that have the property that I can add them together and I can scale them. Basically, I mean, I can multiply them by something like 2, make it twice as big. But here, the numbers can be either real numbers or complex numbers. Another feature that Hilbert spaces have is that they actually have a ruler and a protractor installed so that whenever I use the ruler and whenever I use the protractor, that agrees with the Euclidean geometry that I know and love and live in. Now, I should just remark algebraically, when all the numbers are complex, this requires a certain amount of care. When all the numbers are real, it's just the old Euclidean geometry we know and love. I should also remark that if I was doing quantum mechanics for physics, infinite dimensional spaces would come up all the time. And when they do, they cause all sorts of technical problems. And so physicists insist on this other technical condition called metric completeness, that we don't need to know what it is because they need to have it in order to have their infinite dimensional spaces behave the right way. But in the finite dimensional world of quantum computation that we live in, this condition is always satisfied. So please allow me to pick up the rug and sweep it under it. Thank you. Okay. Boy, it's really interesting how my computer sometimes likes the arrow, sometimes doesn't. Now, I should say that these physicists, like the engineers, are kind of like the French. They have a different word for everything. And so when I, as a mathematician, would say, I am adding these 2 things together, they like to say, I'm putting those 2 things into a superposition. This is the origin of the common phrase that a quantum object can be 2 places at once, which of course does nothing but complicate quantum relationships, something I'll go into maybe in another talk. Okay, so this leaves the word projective. For vectors now, what are those? Those are those locations. Vectors are the mathematical word that we're using for something that describes something that can be added and scaled. So I'm going to just use that from now on. So what's a projective vector? Well, vectors are projective when we don't care about scalar multiples. In other words, if I have 6 times a vector, I regard that as the same thing as the vector, as long as 6 isn't 0. I don't allow 0 times a vector because that always gives me the 0 vector. And so that doesn't count. So that means if I have a non-zero vector and I have a second non-zero vector, and the only difference between them is that one is a scalar multiple of the other, then I regard them as projectively the same. Now, again, we need terminology for all of this. This scalar is called a phase. And we would then say our coordinates are phase equivalent, when they only differ by a phase. So, coordination axioms say that what? Each state of a quantum system is represented by such a vector. That's why we say things that up to phase, this object is this other object. What that means is that one is a scalar multiple of the other. For example, when we talk about our state heads, which I wrote as a vector there, having one head and no tails, well, that state heads is represented by any of these other scalar multiples of it. All of them are perfectly good ways to indicate or coordinatize the state heads. Now phase. I should tell you that all of these physicists who thought this stuff up in the late 19th and early 20th century, they were all amateur musicians. And so the word phase comes from music. So here's the sound wave. Just, I thought I'd let, here's a picture of one. There are three things that characterize a wave, a sound wave like this. One is the amplitude or volume. The other is the frequency or pitch. And the third one is the phase. That's the starting point. The phase being 0 here, that shows you by my little arrow that this sound wave is starting right there at the origin, okay? Well, here is now this sound wave phase shifted. So what I've done is I've taken a unit complex number and I've multiplied the input by it. And what that does is it leaves the amplitude the same, it leaves the frequency the same, but you can see by the red curve, it starts not at 0, but it starts over here at 0.72. Now, of course, if these were two independent sound waves and I was listening to them one at a time, my ears couldn't tell the difference because they're appearing at the same volume and with the same pitch. Hearing a continuous wave, I can't tell at what part of the wave it starts or stops. So this is why this equivalence up to multiplying by a unit complex number, i.e. changing things by an angle, is called phase equivalence, because just like sounds, if two of these states differ by a phase, well, then they sound the same to a physicist's ears. Okay, so now we just need a couple other things. What just happened there? Well, we're talking about something called complex projective space now. Being a mathematician, I'll use my words rather than the physicist's words. And that's what that CP means. The 1 means this is the complex projective line. So what I've done now is I've taken two-dimensional complex affine space and I've what we call mod out, in other words, make equivalent by non-zero scalar multiplication. That forms one-dimensional complex projective space. So what do the coordinates look like that? Well, these are vector spaces, so we like to have a base. This is something we can write everything as a linear combination of. So the standard basis, which for us is the orientation basis, looks just like this. That first one is heads. The second one is tails. So 1 heads, 0 tails, 0 heads, 1 tails. Now, this is kind of a cumbersome way to write them as columns, especially when rather than a bit with 2 things, it's a dit with D of them. And so there's this nice thing, this nice alternative notation that the physicists use, thought up by Dirac. And so heads, we write, and now it looks like a bit. We write that as the basis state 0. That's something called a ket vector, because it has a bar and a bracket. And then the other one, tails, 0, 1, that's the other ket vector, 0, 1. And so these are what we call the basis states, the north and south pole of our block sphere, because any vector is a complex linear combination of those. So in other words, they look like this. Here's my vector. It's a complex number alpha and beta. So that's alpha times heads plus beta times tails, which in a Dirac notation would be written as you see there on the left. Any questions on this? Again, this is probably something some people have seen. All right, so the point here is that what quantum mechanics says is that physical properties, orientation and such, they're in one-to-one correspondence with these bases whose elements are mutually perpendicular. Well, that's exactly what happens here. If you would like to know the cosine of the angle between them, you just multiply these two numbers together, and then you multiply the second entries together, add that up, and since you get 0, the cosine of 0, the angle that has cosine 0 is pi over 2, a right angle. And so these two gadgets are mutually perpendicular and have unit length, the length being this number squared plus that one squared. So those gadgets are the things that correspond to physical properties, like orientation, or temperature, or color, or charge, or shiny versus dull. All of these things are manifested themselves by these basis pairs where the two elements have length 1 and are mutually perpendicular. All right, so now that we know how to keep track of states, how do they evolve from one state to the other? Well, they do that in 3 ways. The first way is by time evolution. Now, time evolution of states in a quantum system is governed by a second-order partial differential equation discovered by Schrodinger. But fortunately, given the time frames that we use in quantum mechanics, this never has a chance to occur. And if it did, we would just regard it as an error and appeal to an error-correcting code. So thankfully, we can throw this one away. The second way states can evolve is a physical action. Ooh, I could turn it over. I could perform flip on it. I could do something else to it. I could take the state heads to the state heads plus tails, or heads minus tails, or 6 heads minus pi tails. I could do any of those things. These things, these operations that correspond to physical actions, are called unitary operations by the mathematics community, which me being part of, I'll continue to use that language. Now, the other way, and the surprising way that a state can evolve, is if we look at it. We call that quantum measurement. And what that does is that produces one of the basis states. You see, I can never see one of these superimposed states. They're not visible. If I look at it, it turns, depending on what device I use, it turns into whatever basis state it wants to. If I look at a quantum superposition with respect to orientation, I'm going to either see heads or I'm going to see tails. Precisely how that works, we'll talk about in just a little bit. I'd like to go back up to the physical actions if I could for just a minute, because physical actions tell us how to do quantum computing. So a quantum computational unit is a qubit. We've been talking about qubits. They have 2 pure basis states, heads and tails in the case of orientation. We can have qtrits. They would have 3 basis states, left, right, and middle, if you like. That would be a qtrit. In general, we have a qdit. A qdit then is what? That's a vector in the state space. And that is, of course, a what? That's a complex, projective, d-1 dimensional Hilbert space. So quantum computation happens when I have a qdit and I apply a unitary matrix to it, something that Merrick will call a quantum logic gate. If I have a bunch of quantum logic gates and I string them together by quantum channels, this collection of quantum logic gates is something that we call a quantum logic circuit. You're going to hear a lot about those in 2 weeks' time from Merrick. So here's just a couple. You might be familiar with these. We saw this one last week. Here's the quantum NOT gate. So that horizontal line is the channel the qubit follows. The NOT gate is in the middle. And so what does that do? Well, suppose I had a qubit in state 0. Well, NOT works like flip. As that qubit goes through there, the zeros change to ones, the ones change to zeros, and the coefficients stay the same. So quantum gates frequently need to be controlled. That means that they have a control on them. The control decides by evaluating a control bit whether to turn the gate on or not. So this is the controlled NOT gate. So there would be a bit for the first line, that's the control bit. That would be in some state A. And the action bit, the bit that's being acted upon by the gate, that would be in an initial state B. And then running in through the gate, well, that black circle says that the gate turns on according to the highest signal value. So in our case of a quantum bit rather, that's 1. That's the highest signal value. And that produces something called the exclusive OR of A and B, XOR. So, this is how to get the XOR relation to happen on the target bit. If that circle at the top was an open circle, control would be by the lowest signal value. And in this case, that would be 0 mod 2. Okay, let's go back now to quantum measurement. Now, quantum measurement says that, well, if I have a basis, that's a physical property, remember, I can measure my qubit with respect, or my qubit, with respect to that property. And what I will see is one of the basis states. In the case of an orientation qubit, I'll see it in state heads or in state tails. That's what I'll see. That's what I will observe. Now I'll see those pure states by a particular probability. And that probability is determined by how much of each pure state is in the superposition, where how much talks about the length of each component. So if you think of the state as being a vector, and the basis states as being the two sides of the triangle that support it, well, the more length of one versus the length of the other, that's just the probability that that first basis state will be the one that you see. Now, precisely, we can give you the actual formula. So if I have a 2-state quantum system like the one we're looking at, the basis we'll just call X and Y. If I observe the quantum supervision, alpha X plus beta Y, well, I'll see X with the length of alpha squared, alpha is complex, remember, over the square of the length of the whole supervision, and I'll see Y with the other probability. Notice the two probabilities add up to 1. And so basically what that says is that when I look at a quantum bit, what I'm really looking at is something the computer scientists call a probabilistic bit. In other words, I see 0 with probability P, and I see 1 with probability 1 minus P. And so that leads the information theorists to call quantum measurement this way. And that is you can only extract a probabilistic bit's worth of information from a quantum bit. Another way to think about this is that at the North Pole, at the South Pole, I see with 100% probability either a 0 or a 1. And each circle of latitude measures out with the same probability. So in other words, if I think of the sphere floating in space and I project that across to a line segment between 0 and 1 running vertically, then each circle of latitude maps to the same probability P for observation. So a quantum bit is a more random probabilistic bit. This is how you kind of get a feel for these things, is that there's this information stored in quantum bits that is tricky to extract, because you can typically only extract classical probabilistic bits worth of information out of one. Okay, we now have all the tools to figure out and really appreciate Q's beautiful scam on Picard. So since this is a postcard from Mars, I'm having Marvin bring it to you. So what does Q know that Picard doesn't? He knows that our coin is a quantum bit with respect to orientation, and it has way more orientation states than just heads and tails. Now, he also knows how those states look. They look like superpositions of heads and tails. Any combination alpha times heads plus beta times tails, where A and B are complex numbers. He also knows that Picard can never see these states, but rather, every time Picard looks at one, it will change into the state H or the state T with probabilities determined by alpha and beta. Now, for H plus T, you can easily see that each of those probabilities is exactly 1/2. Continuing on, Q also knows that there's a lot more things he can do to that coin. One thing he can do is something called the Hadamard transformation, or the Hadamard gate. And what the Hadamard gate does is it takes heads to the sum heads plus tails, and tails to its orthogonal complement, heads minus tails. It also has the great property that, just like flipping a coin over, if you do Hadamard twice in succession, well, up to the phase 2, you get the same result as the classical identity, which is, of course, no flip. We like to say that Hadamard is its own inverse. If you have Hadamard and you'd like to undo it, just apply it a second time. So, Q's strategy is now pretty easy. On the first move, here comes the coin. It's starting off in state heads. So the first thing that Q does is to place the coin into the state heads plus tails. Why heads plus tails, I hear you ask? Well, that's because Picard is now toast. It's because heads plus tails is what we call an eigenstate for either of Picard's actions. In other words, as long as Picard only does the classical actions flip and no flip, he cannot change the state heads plus tails at all. No flip leaves heads plus tails alone. Flip turns it into tails plus heads, which is, of course, heads plus tails. Now, of course, all Q has to do is to apply a Hadamard a second time, and the coin's back where it started from, which is heads. Now, heads is a pure state, so every time you look at it, you'll see a heads 100% of the time. So that means Q wins every time. Picard has no chance. But the best part in my mind is that this is all completely undetectable by Picard. Because if he takes Q up and looks at it, it's in state heads plus tails. Well, half the time he looks at it, it's heads. The other half the times he looks at it, it'll be tails. So Hadamard, in fact, measures out exactly the same as if Q had been using his classical 1/4 no flip, no flip, 1/4 flip, no flip, 1/4 no flip, flip, and 1/4 flip, flip. That strategy, which is done entirely classically, and the quantum strategy, Hadamard measure precisely the same and are indistinguishable by any external observer. Okay, so here we are. Here we have, by access to quantum strategies, what we're seeing now is that a player can have an insurmountable and undetectable advantage over a classical player. So this is a good time for a deep cleansing breath. And does anybody have any questions? Like I say, I can't see the chat. So if you ask me a question on chat, please just chirp up and ask it now.
Everything is clear for me, Steve.
Great, thanks, Merrick. Everybody else? Happy?
Yep, there's no questions on chat.
Okay.
All good.
Great. I will presume then that everybody gave me the response joy. I'm a child of the 80s. So when I ask a class or a lecture audience, happy, I'm expecting the Ren and Stimpy response, joy. Sorry. We'll move right along. All right, so I promised you now what a more detailed analysis. I mean, people can say, well, that's great. Well, what happens though if quantum players line up against each other? Well, we'll look at that. But in order to look at that, I have to teach you a little classical game theory so we can develop some terminology. And so I might as well go through this game theory by explaining what Picard thought he knew about the game that he was playing with Q. Okay? Now, the thing that you should know is that game theory is a legitimate branch of mathematics. And it's really optimization in a way, because it talks about the decision-making process. And so it also arises all over in when some agent's actions depends on what they perceive another agent to be doing, okay? And so game theory can be really confusing to some people. And it takes a little bit of thinking on your part to keep things all straight. Now, I should warn you that game theory is just full of what seems to be circular reasoning. I know that she knows that 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 I know that she knows. This makes some people very uncomfortable. And you really can't get away from it, because if you're playing a game, what you might decide to do might depend on what your perception of what your opponent is going to do, and vice versa. And so because of this, what you look at in game theory, you find all these things that are regarded as counterintuitive, or that to many people appear paradoxical to what they would call common sense. Okay, now we're going to be talking about probabilistic outcomes. In other words, such and such a percentage of the time you're going to collect so much money. So how do I evaluate those? And this, we use a tool called expected value. This is probably familiar to most of you. This is just the long-term average. Do this thing over and over and over a gazillion times. This would be the average of what you got. I like to give a little simple example. Suppose we're going to flip a fair coin, and kind and generous man that I am, I'm going to give you $1 for every time a head appeared, but I'm not going to give you anything at all if a tail comes up. So what would be the value to you of each flip of the coin? This is what we would call the expected value of the coin flip. Well, this is easy enough to do. You take the probability rather of an event times its reward, add them all up over all possible events. And in our little example, it's 50 cents. I bet most of you knew that. But you should realize that it does not say that you'll get 50 cents on any given flip. You get either an entire dollar or you get nothing at all. Most of you also would know is that you wouldn't necessarily get $5 for 10 flips, but over 1 million flips, you'd be pretty close to getting $500,000. And 1 billion flips, you get close to Pentagon money, which would be $500 million. Okay, this is a consequence of something we call the law of large numbers, which is the most immutable law I know. So that just says that the number of repetitions of something goes up, the closer the average result to the expected value is. So, and again, I like to explain this to people who aren't familiar with it by saying that it wouldn't surprise you in our little game if after I flipped the coin 10 times, you'd only won $3. Or if you were lucky enough to win $7, you wouldn't think anything was too unusual. But just like Picard, after 1,000 flips, if you only won $300, you would likely start to think, is this coin not really fair? In other words, the probability of heads isn't really 1/2. And if after 1 million flips, you'd only won $300,000, you would probably be convinced that, no, the probability of heads is really only 3/10. This is something in mathematics we call a stochastic limit. Okay, so you can always play games against crazy people. You play games against crazy people, they do crazy things. You can't predict this, so you can't react against it. So all you can do is roll the dice and hope for the best. But against a rational player, someone who has preferences logically determined at, you can do something about. So economists and game theorists always talk about what does it mean to be a rational player. Well, rational players do certain things. Well, when they play a game, one of the things they do is they try to find something that Q had, which was a winning strategy. In other words, something that pays them every single time and gives them as much money as possible, or as much a reward as possible, if money is not what you're playing for. Now, of course, not every game has such a thing. So failing that, the rational player would say, well, there are no winning strategy here. Can I at least guarantee I won't lose too much? This is something called a security strategy. In other words, you will get at least this amount every time you play the game. A strategy that guarantees that is something called a security strategy, or is referred to as being secure. Now, on the other hand, maybe there is no winning strategy, maybe there is no security strategy, but you are a pretty good reader. You could pretty well know what your opponents were going to do at any given time. In that case, what you're looking for as a rational player is something that we call a best reply. That is a choice of your own strategy that delivers a payoff as big as possible. In other words, as great or greater than any other of your strategic choices would deliver. As it turns out, this best reply notion has legs. And it allows us to identify when a game is in balance. And that's something called an equilibrium. So a game is in balance when you have a profile of strategies such that each profile, each strategy that you choose is a best reply to the strategy choices of the opponents. So what that means is that no player can do better by unilaterally deviating from the equilibrium strategy. In other words, if they choose some other strategy, they might be able to do as well, but most likely they will do worse. This is why the game is in balance. Nobody can move without upsetting the balance of the game. Well, for two-player games, that says that if I have an equilibrium strategy, well, that strategy is secure. In other words, if I play an equilibrium strategy, either my opponent has a best reply to it, or my opponent doesn't. If my opponent doesn't, I make more than I would if he had a best reply. That would minimize my return. And so that means that an equilibrium strategy in a two-player game is a secure strategy. On the other hand, we're going to be looking at poker in a little bit. What if there aren't any equilibria either? And what if, in such a situation, I had an opponent who is really, really good? And that opponent could sort of look at me and understand what I would do in any given situation. What do I do then? Well, fortunately, there is a way to beat this, and that is to turn the game over, basically, to the randomness god. In other words, you don't make strategic choices anymore. You have some random element, a coin, a deck of cards, a roulette wheel, a lotto board, some random variable make your strategic selection for you. Because while a really good opponent may be able to read you, no opponent is going to be able to predict what a truly random variable is going to turn out as. Okay, this is something called strategic randomization. So I'm going to show you how it works in practice. So you might want to take a deep cleansing breath while I wet my whistle. So this is a game you may have played as a child called Odds and Evens. Each player puts out 1 or 2 fingers. If the total is even, one player wins. And if odd, the other player wins. Simple enough. Now, this is something that if you're an alert player and you keep an eye on your opponent, you can discover this interesting fact about humans is that humans are seldomly random. Typically, they have patterns that they follow. Oh, they're going to put out an odd number 6 times in a row, followed by 3 even numbers, followed by an odd. This is something that you can discern by observation. So here you are. You like to play this game. Someone challenges you to the game, and they know that you know that they're really good. And so you're not willing to play them heads up, but they are so confident that they can beat the pants off of you, they're willing to give you an edge in the game. In other words, I'll pay you $51 when you win, and you only have to pay me $50 when I win. Now, on the other hand, you think your opponent might be better enough to overcome this advantage. Well, how can I now win? Well, what we do is we use strategic randomization. In other words, all I'm going to do now is flip a coin. This is now my random variable with probability 1/2 to have a heads and 1/2 to have a tails in a way that my opponent can't see, and let that determine whether you put out 1 finger or 2. You've taken the decision completely away from yourself. Well, notice here that you've completely eliminated your opponent's ability to outguess you. You don't know what you're going to play. How can they guess what you don't know yourself? Moreover, your long-run expectation, because of the edge they gave you, is in fact positive. You have actually a 50-cent expectation per bet. See why? Well, I'll let you ponder that. But the important takeaway here is that by strategic randomization, not only have you overcome whatever playing advantage your opponent had, you've also given yourself an unbeatable edge over the long run. This is pretty good. Okay. So what this means is that we're going to make our games bigger. How are we going to make our games bigger? We're going to make the strategy choices bigger. Instead of my strategy choice of I'm going to put out 1 finger or I'm going to put out 2 fingers, my strategic choices are expanded to all the probabilistic combinations. I'm going to put my finger out as 1 finger with probability 1/2, or 2 fingers with probability 1/2, or 1/3 and 2/3, or 1/6 and 5/6. Any of them would work, and all of them become a new strategy for this game. So the game suddenly got a lot bigger. Okay, so how much bigger did it get? Well, the strategy spaces have now been enlarged from the original strategy space X to all of the probability distributions over that space. Well, that's something that we call del S. And that's just because in the finite case, they make little slices through the front octant that looks like a simplex. Game theorists call these the mixed strategies for G. And we get the outcomes in this new enlarged game. Well, now they're not definite anymore because the outcomes aren't definite. The outcomes are probabilistic, so we determine the payoffs by expectation. So game theorists call this new game by, logically enough, G-mix. The key point here is that the original pure strategies have not gone away. In other words, if I wanted to know what mixed strategy corresponded to the pure strategy of putting out one finger, all I have to say is, this is the mixed strategy, put out one finger with 100% probability, put out two fingers with 0% probability. So the original strategies have not gone away. And if I wanted to, I could play the original game in this new context. This is what game theorists called recovering the original game. And if in fact you can do this, we say that you've now taken your game and you've enlarged it properly. And you can thank now the British for that. All right, so let's see how this would work in pictures. So running down there along the bottom is our game G. Here is the product of all the strategy spaces. So those are all the profiles, S1, S2, S3, of the strategy choices of each individual player. The game maps it over here to outcome spaces. In other words, here's the payoff to the first player, the second player, the third player, the fourth player. So our original game G, you can think of an arrow that goes this way that I noticed my computer has put the head over here for some strange reason that perhaps Merrick will explain to me later. Okay, so the strategy spaces are now enlarged. Each individual strategy space has become the probability distributions over that strategy space. And again, I have a profile. I have one for each player. That's what that product sign means. Now, I decide that the players determine their strategic choices independently. And so that means that in order to get the distribution over the profiles, that all I have to do is multiply together. That's what it means to be independent. Otherwise, we have something that is called correlated, and I have some other way of pushing these probability distributions over the individual strategies into a distribution over the profiles of strategies. So having done that with the product map, I then replace those strategies by their payoffs. That's the image of G. And I get a probability distribution over the image of G. The mathematical term for doing that is called a push out. I follow that by taking the expectation of this probability distribution over the payouts, and that gives me the expected payout. And so if I now think of this as my new strategy space, and I think of this as my outcome space, I now have the new game that I call G-mix. And what this little diagram means is that if I follow the arrows through one path from start to finish, that's the same as following arrows on the other path from start to finish. So this is what this little diagram means. Now, the whole idea of being proper means that these original strategies live up here. So in mathematics, we call that an embedding. So that's a embedding for each player, hence the little product symbol. That maps the original strategies into the probability distributions. And then the fact that this is a proper extension of the game is because if I take G-mix and have that following this embedding, what I get is the original game. That's what we meant by recovering the original game. So this is kind of a flow chart of how we made the game bigger by strategic randomization. So this is a good time to ask for questions. We good? Okay, by your silence, say that you want me to go forward. All right, Well, at long last, let's talk about poker. Yay, let's have some fun. So let's say we're playing Texas Hold'em, and after the last community card is dealt, the board is complete, and that board looks just like this. Hey, there's a straight on the board, no possible flush, no possible pair, so that means the highest possible hand is an ace high straight. So I now have to worry about whether or not my opponents have an ace or not. And let's suppose that I've played with these people long enough that the probability that they've lasted this long, if they didn't have an ace, is exactly 50-50. Further, let's consider the betting, and we'll keep the numbers small just to make life easy. The betting up to this point is an ante of $10. Those are all the previous bets. And that a player can now bet $15 at the pot. Moreover, at the end, when all the betting is through, every player holding an ace gets an equal share of the pot. And if nobody holds an ace, everybody who called will get an equal share of the pot. So this is what happens in your favorite poker room every Friday night. All right, so let's talk about strategies and payoffs. So players now in their hand, in their hole cards, they either have a winner, which is an ace, or a loser, which is basically anything else. Further, after we throw away the losing strategies, for example, if you have an ace and you don't bet it and throw your hand away instead, that's what passing would be, you can always do better than that. So no rational player would do that. In a two-player game, our game takes on a particular form where each player has two strategies. The opening player could either maybe run a bluff or play directly. So run a bluff would mean that you would bet no matter what you held. Play directly means that you would not bet if you had a loser and you would only bet a winner. For T1, that's play directly. You would only bet a winner. You would fold the loser. And T2 is, oh, I'll call that obvious bluff. That means you'll bet no matter what you hold. So when you have a game like that, here's what the payoffs to our little player look like. And in fact, what we see is that player one, this being a zero-sum game, player one has the advantage in this game. In that 5/4 of the time, they'll win, and minus 5/4, they won't. So these are the various payoffs. So this is actually a very well-known game to game theorists. They've been playing it for 125 years. And it's called simplified poker. Now, you may notice, oh, I should go back to that. You may notice there is no Nash equilibrium here. Okay, when you look at this player, there is no equilibrium strategies because a best reply to S1 is T2, but the best reply to T2 is S1. Similarly, the best reply to S2 is T1, and the best reply to T1 is S1, okay? And so there are no Nash equilibria in simplified poker as it presents there. Okay, well, enter John Nash in 1957, who says that, oh, if the set of strategies are finite, then if I mix up the game, I can always find a Nash equilibrium. In other words, there might not be any balances in the original game, but there is always at least one balance in the extended version. Well, for simplified poker, what does this represent? This means that these are what we call the optimal bluffing and calling frequencies of the players. So basically, these frequencies tell us how often should player one bluff and how often should player two be the policeman and call that possible bluff down. And when you crank up the numbers, the optimal bluffing frequency is 2/3. And for player two, the optimal calling frequency is 1/3. And so this means that playing this equilibrium yields 5/6 to player one and an expected payout of -5/6 to player 2, poker being a zero-sum game. In other words, all the payoffs have to add up to nothing. Happy, happy? Okay, by your silence, we'll go forward.
Yes.
Well, now, oh, yes, question.
No, I say I'm happy.
Oh, you're happy. Great. Was that a question by somebody else? I'm happy to answer questions. Okay, everybody's happy. Well, now you see, you want me to embed this in quantum technology. Of course you do, because that's why we're here. So I would like to take a finite game G, and I would like to extend G to a new game we'll call G quantum, GQ. Well, how do I do that? All right. Well, okay, let's talk about what we need to have. What we need to have is a collection of quantum strategies. So in the original game with Picard and Q, Q's quantum strategies consisted of all the unitary matrices. Well, up to phase, all the special unitary matrices. So these are for each player, they have a set of what we would call the quantum strategies. Maybe these are quantum superpositions of classical strategies, or maybe like Hadamard is a strategy that has nothing to do with any of the classical strategies whatsoever. So that's the first thing we need. The next thing we need is some way to take a profile of quantum strategies, that's that product symbol again, and get a quantum superposition over the image of G. Well, the image of G are the payouts, and I'd like to lay my hands on a quantum superposition of the payouts. We call that function a protocol because it drives the game. All right, well, now we want to actually compute payoffs. So if I start with a quantum superposition, if I apply quantum measurement, which I've written here as Q-measure, what I get then is a real live classical probability distribution over the game's classical payoffs, which I can then apply expectation to get a real live expected payoff for our game. Steve, please draw me a picture. Well, let me talk first about what it means to be proper. That means that the original game survives, and what it means to be complete. That means that the mixed game survives as well. So the Qs are the pure quantum strategy sets. So I need to have an embedding of the original strategies into the quantum ones. Believe it or not, this can be tricky to do. And it has to have the property that if I go by that, go by these embeddings, follow it by the quantum game, I get the original game. That's what it means to be proper. For the mixed game, well, that means I need an embedding of the probability distributions. And that means that to get the original game back, I need to take GQ following the embedding, then that has to be the original game G. Then GQ is said to be not just proper, but complete, because I can, if I want, by sticking to the image of EI double prime, play the mixed game. If I stick to the image of EI prime, I can play the classical game. That's what it means to be proper and complete. And all of that fits together in this hideous diagram. Oh, scary. What does this diagram show us? Well, if you look here on the floor, you will see the diagram for mixing. Here it is. Here's my original game. Here's my G mix. Here's my probability distributions, being independent, coming to these, pushing out by G to here, expectation down to there. There's our friend G mix, okay? So here then is our product of probability space, of quantum strategies. Here's our protocol that takes us over to the quantum strategies. Quantum measurement takes us down to a probability distribution over the image of G, and then expectation takes us down here to the payoffs. That's exactly what we meant by the quantized game GQ. And now for proper and complete, here are the embeddings. If I have this embedding from the original product of strategy spaces up into the product of quantum strategies, which I then follow by GQ, I should get my original game G. Ditto, if I start here, that's proper. For complete, if I take a profile of mixed strategies, run them up here to the profiles of quantum strategies, follow that by GQ, well, what I should get is exactly the original game in its mixed form, G mixed. So one of the things we see is that a complete quantization is proper. Another thing that we notice is that finding a proper quantization in mathematics, this is a problem we do all the time. I have some function defined on a subset. What I would like to do is extend it to a much bigger domain. So it's not a problem that mathematicians and by extension game theorists aren't familiar with. Any questions here? This is kind of a complicated picture.
I guess I have a question on what
Sure.
it would mean to have a so I've learned about non-complete problems. So what would it mean to have like a non-proper game?
Okay, well, actually, the original way that was proposed to, quote, quantize poker, I had exactly that property, is that this gadget did not exist. There was no way to take the original strategic choices and find them in what was called the quantum strategic choices. There just was no way to do that. And so the game theorists looked at this and said, well, you can't say, yes, you're using the game G in the definition here, but this game that you are calling GQ really has nothing to do with G, because I can't play it. If I'm sitting here with these quantum spaces and there is no embedding like this, then there's no way to play the original game in the context of this one. And so that's kind of what it means when you have the problem ill-posed. It means that you don't have enough data to run the original solution architecture. So typically you have solution architectures to problems. And if you can't run that architecture, that's what we say that the problem is ill-posed. Is that helpful?
Yep. Yeah, a bit more, just so I'm kind of getting an understanding of the picture with the definition of what you just said, so it makes sense.
Okay, great. Anybody else? I live to serve here, folks. Okay. All right, so having said all of that, you know, we can randomize yet more. What? Yes, folks. See, what have we done? We took a game and then we classically randomized it. Okay. Now what we've done is, using quantum mechanics, we've quantized it. Well, that's just another game, ladies and gentlemen, which means there's no reason that I can't take a probability distribution over the quantizations. Yes? So on top of that whole picture, sticking out as a big old flange, here's GQ, here's our quantum game. Well, I can take the probability distributions over those quantum strategies, you know, even if it's just some hideously described density function, I can still do it. And if they're independently chosen, I can form their product. And once I form their product, I can push out by the original game GQ. And that gives me a perfectly good probability distribution over the image of the quantum game, which I can then apply the expectation operator to and get a real live game that I call G mixed Q. Randomization upon randomization upon randomization. What we're seeing now is what was not observed until the advent of quantum technology, quantum computation technology, was that there are classical stochastics. This is the way I randomize, using which, and if I had only a finite set I was randomizing, this would be something that we would call a real convex linear combination. In other words, the coefficients are all real numbers, they're all non-negative, and they add to 1. This is something called a real convex linear combination. Follow that by expectation. I have modern probability theory. This is something that we call classical stochastics. What's come out now with the advent of quantum technology is that there are these higher orders of randomization. The first one given by superposition, that's what you can think of here. And then I can actually take mix over the superpositions. So doing this, we realize there's this higher order of randomization that is essentially superposition followed by quantum measurement, followed by expectation. And this is leading up to a brand new field called quantum stochastics. And this is something that has arisen in the last 5 years. And quantum stochastics were inspired by this development by the quantum game theorists of looking at higher and higher orders of randomization beyond the classical, all made possible by communicating over using quantum technology. So how do we do this for real? This is something called the Isert, Wilkin, and Lewinstein protocols. Game theorists like to call this mediated quantum communication because it generalizes medium classical communication. So they, in about 2003, they gave a whole family of protocols so that we could produce this game quantization that we've talked about for the classical two-player, two-strategy games, like the one simplified poker we've been looking at. Now, these protocols require this game to be played under the auspices of a referee. And this referee communicates with the players over a quantum channel, which means that the players and the referee can actually send real superpositions of a qubit back and forth between each other. The players not between each other, but the referee and the players can do it. All right, so basically what happens is each player gets a qubit. They're sent in a joint state, a quantum superposition of the joint states. So that means I've got the two together. So we get these by tensor producting the two state spaces together so that the phases will pass from one side to the other. For two players, these things look like this in the Dirac notation. And you may have noticed I've done something tricky, and that is I've started to run the scalars on the right. And the reason I do that is that when I apply a quantum gate, that's a function, I'm going to want to apply that on the left. And so I do not want that phase or scalar to be in the way. What do I apply first? Do I apply the gate or do I apply the scalar? So to keep getting away from those issues, because very soon order will become important, I've started to write all my vector spaces as right vector spaces. Merrick is rolling his eyes right now. He's been listening to me talk about this for a decade or more, and he still hasn't started writing his vectors, scalars rather, on the right. Sorry, Merrick. Anyway, each choice of the alpha, beta, gamma, and delta, that gives me an additional initial state that the two qubits the players are going to use are in. And so each one of those produces a way of quantizing the game, a different protocol that we call QI. So the referee sends the players the qubits. They act on them by a unitary matrix. The S means special, that means determinant 1. Up to phase in a unitary matrix, and have determinant 1. And then after they've done that, they send the result back to the referee. Now, I should point out to you that while the players have this much larger strategy space, in other words, a whole three-dimensional sphere's worth, now, not just a two-dimensional sphere's worth, they have available to them the classical pure strategies, which still sit in SU2, no flip and flip. both of which are unitary. So the referee takes a look at this. He expresses, he disentangles, he looks at the final state in a specific basis of our quantum this, goes by, applies the quantum measurement, and then makes the appropriate payoffs to the players. Now, all that's well and good. The way that we understand what's going on is to pick a particular protocol. And this was done by Stephen Landsberg of the University of Rochester in about 2005, maybe. And what he looks at is a very specific EWL protocol, because most of the time, the protocols given by the EWL system are not complete or not even proper. But if I choose our favorite state, where the states are correlated to the maximum extent possible, then in fact, we do get a gadget that not only has this really wonderful property that it's proper and complete, but when I follow the protocol by quantum measurement, I actually can get every possible probability distribution over the image of my game. Now, the reason we call these maximally entangled is, notice that if I observe this, whatever I see the first qubit as, I know the second qubit with 100% certainty. If I observe this qubit in this state, and I know that I see a heads, a 0, I know that that second state, whether, 5,000 light years and 10,000 years in the future away, that's the state at the same time. This is what Einstein called spooky action at a distance, and he spent a large part of his life dancing around that. But unfortunately, it's a fact of life that entanglement works, and there are people like Deutsche who use this phenomena to come up with algorithms that have exponential speedups when compared to classical ones. Be that as it may, when I look at these games, he actually determined where the Nash equilibria were. He used something called quaternionic coordinates, which you obtain by Dixon doubling the complex numbers. All right, well, that's a postcard from Neptune, so we won't go there. But on the other hand, that allowed him to say, where are the Nash equilibria? And in particular, there are no Nash equilibria in GQ, but there are Nash equilibria in the mixed quantum strategies. And of course, there, as before, they look awfully familiar. They look like these uniform probability distributions we saw way back when Picard was flipping coins classically, he believed, with Q, okay? And in the process, we see that each player is guaranteed then to get the average of the 4 classical payoffs. But if we apply this to simplified poker, it says that playing the quantized version yields player 1 an expected payout not of 5/6, but of 15/16, a strictly better payout than he can expect classically. In other words, player 1 can do better playing poker over the quantum internet than he can in real life. So what just happened? Let's wrap things up for today. What's the first thing we saw? We saw that if one player has access to a sufficiently large group of strategies given by quantum mechanics, that can have a result in an undetectable and insurmountable advantage, okay? And again, this is because of this higher order strategic randomization given by what we now call quantum stochastics. This poker is that even if both players have access to quantum strategies, you can do better under mediated quantum communication due to entanglement than you can in real life. You can make more money I mean, give me my little quantum Q, my little QMac, Mr. Jobs, give me my QMac with his little bottle of liquid helium and run me my fiber optic quantum internet cable to that server in Barbados, who's the referee, and let me play poker all night long. Thank you very much. I'll be able to do better that way than I can by going down to my local poker hall and playing in real life. Of course, friends and neighbors, your poker hall down the hall, like the one at 26th and 26th and Powell, just down the block from me here, where I am now, those are little tiny poker games. The biggest poker game in the world is given by the stock markets. Wall Street, the London Stock Exchange, Shanghai. And while these people are starting to realize the benefits of quantum communication, which is 100% secure to eavesdropping, they still are pricing securities and equities using classical stochastics. Eventually, folks, the people at Wall Street are going to start to realize that they can package and price securities using quantum stochastics. And when that happens, friends, all I can say is that shark and fish are going to mean whole new things. So that's probably enough for today. You have any questions?
Thank you so much, Stephen. I think we have time for one or two questions.
I'll hop in and ask a question.
Sure.
Stephen, great talk.
Sure.
I can't believe
Thank you.
all the fields you covered in such a short amount of time. I don't really know much about all of this, so this is more of an intro for me. But I did listen in on some of the MIP star equals RE explanations at the last Berkeley gathering. The question I have is, there was mention of protocols and compression and with that proof, and I'm curious how much of what you've talked about, I'm seeing some similarities, especially with recovering original games, because they were talking about compression in that proof. And I'm just wondering if you can speak to any of like the overlap between what you've shared and how that proof has come to be, if you if you're aware of
Sure,
that.
I can talk about that. So let me go back to the appropriate slide. And that's this slide here. Okay. The thing that drives everything in both these proofs is this function, this map here. The fact that this is a product means that this were chosen independently. But in the situation you described and what they described, what we're describing in Berkeley, is that there's correlation between the players. They're cheating. You know, they made a deal in the parking lot. If you do this, I'll do that. Or they're acting exactly as if they had. That's called implicit collusion. That means that instead of getting this very limited sense of probability distributions, which technically are described by saying the distribution is the product of the marginals, they have what's called a partially or partially entangled situation there. And so now the question of faithfulness of this line, like how accurately does it represent going across this way and down, comes into play. And that's what they were talking about. The idea of a protocol is the standard terminology, going from a product of strategies, quantum strategy spaces, to quantum superpositions. That's a standard term. Compression, what they're talking about is how much information is lost by having the correlation occurring here. Is that helpful, I hope?
Yeah, thank you.
Are there any other questions?
I guess I just have one question on that last point that you made. Conversely, would it be possible with the higher order of randomization that you said would be best at maybe beating a game of poker? Would that be possible in larger systems like the stock market to make it seem as if like no one can win in that kind of sense? Where
Oh,
I guess the randomization part of it was the randomization part of it allowed you to win in that specific game of poker, that specific match. But would it be possible if two players were using it that maybe it was there in that picture, but if I guess what would that do if it was?
So what poker is a game is an antagonistic game. That means when one person gains, the other loses. Somebody
Right.
else loses. It's a negative sum because there's always a fee to play. You always have to pay somebody to trade a stock, for example. It's called friction. You always have to pay the rake in a poker game. Of incomplete information. The information is, you know something that I don't know. In poker, that's your cards. I know something you don't know. In poker, that's my cards. And so neither of us know everything. So that's incomplete information and chance. The random stuff happens. A virus breaks out from China and the economy goes to the toilet, right? Random stuff happens, Poker is a model where we can quantify all the variables. So that's why poker is a model for things like the stock market. Basically, any antagonistic game of incomplete information and chance, poker models. And so, yeah, when I can start communicating with my broker a quantum superposition of buy and sell orders, that's going to be a whole different thing than me sending my broker. By the way, what I would like you to do is to buy this stock if it hits that, buy that. See what I mean? All of those markets, once we can communicate over quantum channels, all of those markets are prone to disruption by the introduction of the fact that there are going to be new strategic choices and there are going to be new products on the market that that will have to be valued and have to be priced and exchanged some way because it's a market. And so it's going to be the Wild West.
Yeah, it's exciting.
Yeah, it's great. And the ones that understand this are the ones that are going to do better. The ones that are just kind of in there, the Picards of the world, just, running around under the old rules, they're going to find themselves at a terminal disadvantage. That's the point that I opened with, is that if you're playing one of these games classically and your opponent is playing it in these quantized, where they have access to this much greater range of strategic choices, you're going to find yourself at a disadvantage.
Thank you. That was awesome.
You bet.
Super. I think with that, we'll call it an end. Thank you so much, Stephen. That was fantastic. And
My pleasure.
Thank you all for joining. And
for organizing this.
Thank you. And I hope to see you all again in 2 weeks for the next meeting.
Ciao, everybody.